All right, welcome back to section 5.1. Just to go over the importance of this power functions again. If you have an even power, x to an even number, and you multiply it by a positive number, right, the graph is going to leave the box in quadrant 1 and quadrant 2. And let's see, they're talking about odd right here. If you have an odd power, it's going to leave the box in quadrant 1 and quadrant 3. Now, this whole idea of saying, for example, quadrant 3, what that's said in a very formal manner with this kind of thing. As x goes to negative infinity, meaning as you kind of walk in this direction to the left, the function is going to go down as well. It's going to go to a negative infinity as well. And so as x goes to the left, the function goes down. That's the way this is saying it. I like to say it with two symbols, Q3, quadrant 3. So I'm not even talking about what function this is. I'm just saying this is x to the odd. So it could be x cubed, x to the 7, x to the 11. As long as it's x to an odd number, it's going to do this. Now, we can change that by multiplying it by a number. If I multiplied it by a positive number, it wouldn't change. It would just stretch it. It wouldn't change how it leaves the box. But if I multiply it by a negative number, the graph will change quadrants. And so we know that putting a negative number on a function changes the function, reflects it in the y-axis. And so if I had, and we just saw that, if I had x to the 7, no surprise. But if I have x minus x to the 7, the reflection occurs. Reflect about the... we're saying they're reflected about the x-axis. All right. Well, reflected about the x-axis has the same effect. Flips it this way. So the part that left in quadrant 1 leaves in quadrant 4. I guess we could see it that way. All right. It's going to be important, not just for graphing something like this, but as you can see, even if you add 1 to it, this is a good starting point. Turns out you can add anything to it, and some of what we're saying here is going to be important. But that's for another lesson. All right. They're saying that you can learn a lot from a graph by looking at it. First of all, if I ignore everything in the middle, I know that this polynomial behaves like ax to an odd power where a is positive. And how can I be so confident? Well, it leaves the box in quadrant 3 and in quadrant 1. And you just have to remember, when does a graph, a polynomial, leave the box in those quadrants? When it's behaving like y equals x cubed, which is a positive coefficient and an odd exponent. I'm not saying I know what it is yet. I just know it's odd. All right. So just looking at how it leaves the box tells us something. Now what they're talking about is these intercepts tell us the factors. And we're going to use the zero product property and see how it's factored. Well, if you have the picture or if you have the polynomial factored, you can kind of switch from one to the other. All right, well, they have a lot of other information here, but let's look at what they're telling us. All right, so all of these are equivalent. If r is a 0, that's the same as saying, well, f of r is equal to 0. It's also, if you factor it, x minus r would be a factor. And it's also true that r is an intercept of the graph. So all of these are related. Some of these you're familiar with. We use factoring to find the solutions. So if you were to factor just a polynomial, if you were to factor x minus 1, x plus 2 equals 0, you would know that when you set these equal to 0, you'd get what we call solutions to the equation, and x would equal 1, x would equal minus 2. So we're saying, well, if you know if it's a solution, then you also know it's a factor. So we could reverse this. And if you were to graph it, it would be an x-intercept. We've certainly done that before, and even in this class. And then this phrase, we call it a 0. So calling it a 0 is something that we do. All right. Find a polynomial. All right, so we're not going to be using graphing utilities. That's a graphing calculator or something, but we'll see what they did. All right, but here's a question. Find the polynomial function of degree 3. So they already told us it was going to be degree 3, whose real zeros are these numbers here. Well, we're going to use the factor theorem, and we're just going to take x minus each of those numbers. So if you remember the numbers, they were -1, +2, and +3. So x minus -1 is this factor, x plus 1, x minus 2, and x minus 3. They put the a here as the lead coefficient because you could multiply by any number and you still wouldn't change when the function's equal to 0. So you can't just assume that would be a 1. You might need to put something there. And they're just saying the most generic thing we could put there is just a letter for the coefficient. So what they're saying, yeah, a causes the graph to stretch or compress, but it wouldn't change the x-intercepts. So that's it. Kind of going back to this, it would just be as quickly as wrapping a parenthesis around x plus 1, x minus 2, x minus 3, and putting an a there. And by the way, how do we know this is degree 3? Well, this is this multiplying I was talking about, mental multiplying I was talking about. I wouldn't want you to do the whole multiplication back into a polynomial, but we do know that when we did this x times this x times this x, we would get x cubed times a. And by the way, what would happen at the end? This 3 times this 2 times that 1, 2 of them are negative. I would end with a plus 6. What exactly happened? Well, times a. What exactly happened in the middle would take a lot of work with the distributive property and such. So it's not worth the extra effort to put it into polynomial form, but identifying the first term and the constant might be something we'll need to do. And this was the authors just using a graphing calculator to graph it. They left the a out on this graph just to see what it would look like. And the idea here is, let's say you started the problem here. What if they said, all right, what graph is this? Well, if you know that's it looks like degree 3 or odd degree because of the quadrants it's leaving in. But it's also, it has a 0 or an x-intercept at -1, at 2, at 3. And the question is, could you just take this picture and reconstruct this polynomial? That's another skill we need to develop. So far, I just put a parenthesis around. Notice I didn't put x minus 3 squared or something like that, or cubed. Just assume these were to the first power, and we call that the multiplicity. Multiplicity doesn't give you more intercepts, in other words, the intercepts of x minus 1, x minus 2 are the same as the intercepts, x-intercepts, for x minus 1 cubed, x minus 2 to the 5th power. In other words, in both cases, the graph would have intercepts where this equals 0 and this equals 0. But obviously, putting an exponent here does change something. It has to do something to the graph. And that's what they're saying. That's what we're going to study. So we call this the multiplicity, the number of times the factor occurs in the polynomial. So x minus r to the m would have a multiplicity of m, x minus r to the m plus 1, if it's not a factor. Okay, so they're just saying if m's the highest number, then it would be a multiplicity of m. Some books say multiple root, yeah, or root of multiplicity m. All right, so can you see it? You can think of this as x minus 0 to the 3. So 0 has multiplicity 3. This is x minus 5 to the 1. So 5 has a multiplicity of 1. And this is x minus negative 1/4 to the 4. So negative 1/4 has a multiplicity of 4. So identifying the multiplicity is, well, pretty simple if you have it factored because it's visual. You can see it. Now, I said that it also changes the graph. So how does it have an impact on the graph? There's a multiplicity, make a little table. There's one of the zeros or x-intercepts is 3, and it has a multiplicity of 2. And this would suggest that, it's 0 when x equals negative 4, and it has a multiplicity of 1. And we'll just go to the graph that they'll give us, hopefully, to see what we can do with that. I really want to get to the graph. No, let's go, wow, this was so much work. Okay. I think we could have spared ourselves all of this work if I just tell you what's going to happen. All right. So what's going to happen is, let me just, you can peek at that, but let me go back to where this all started. All right. So here's the function, and I'm going to draw my graph right here. So what do I know? I know that 3 is a 0, so 1, 2, 3. I know that negative 4 is a 0, so 1, 2, 3, 4. I know that if I were to multiply this out, this would contribute an x squared, and this would contribute an x. So the problem starts out as x cubed plus something. Let's go ahead and do that other thing I was telling you about. If I were to square the negative 3, I'd get 9. Multiply that by 4, and I'd get positive 36. So this is my mental multiplication of this. And there's a reason why I'm doing this. This is all I need to graph this thing. I know what happens with x cubed. It leaves the box in quadrant 1 and quadrant 3. What's new, and that I haven't told you, is, oh, by the way, I also know that this is the y-intercept. Even if I don't know anything else, all the other terms have x's in them, so I do know f of 0 makes all of these middle terms 0, even the one that had x squared or x. But when I put in a 0, I get 36. So I know there's going to be the graph's going to be up here at 36. So I'm going to go ahead and just say the graph has to do something like this. It has to cross at 36 and has to come through here and cross that point. I'm using the word cross because that's what graphs do when you have a multiplicity that's odd. The graph will cross at that point. What do graphs do when the multiplicity is even? They touch, but they don't change quadrants. So it touches the x-axis, but it doesn't change quadrants. So honestly, that's as good of a graph as we're going to get in this class. Intercepts are where the graph either touches or crosses. We know that with mental multiplication, we can get some information. So what does the author do page after page here? So the author finds the intercepts. The author does some analysis about when the graph is positive, when the graph is negative, when the graph is zero, essentially solving certain inequalities. It's not that you can't do that, but it might be information you don't need. In fact, almost always information you don't need to get a decent sketch. So the author went through the whole idea of if you have these 2 points and you test a point here, this is positive, it's also positive, and negative. So below the x-axis, above the x-axis, above the x-axis. I'm not saying that these are not useful tools, but maybe not necessary for this problem. Then the author decides to put it all together. All right, the points, this point was 36, like we calculated before. We know it's going to leave in quadrant 1 because of the x cubed being the leading coefficient or the leading term. And it's going to leave the box in quadrant 3. And now, things like this were just, the rest of this graph, these points were just things we're not going to find. Because they really aren't part of a normal graph like this. They just plotted some extra points. Little bit of overkill, but books deal in computer-generated images. We deal in something more hand-drawn and a little quicker. So to put all this another way, I can tell the graph is positive if x is greater than 3 because I can see it. I can tell the graph is positive in between here because I can see it. And I can tell the graph is negative here. In other words, which of those am I going to use? Am I going to use the graph to tell me where it's positive or negative? Or am I going to calculate all of this? I have my preference. And that is what I sometimes call a sloppy graph. All right, but here's a nice graph generated by a computer to confirm everything. Now, turning points are going to become a big deal in calculus, and they're going to be our Achilles heel in this class. So notice how a degree 3 problem can have at most 2 turning points. This is turning point 1, not negative 250, but something kind of close to it. And this is another turning point. So I said they're our Achilles heel. We can find turning points sometimes. When a turning point coincides with an intercept, we can find it. We can find turning points for parabolas. And that's about it. It takes calculus to find this turning point. We don't know where it is. We just know there had to be a turning point because there's no way to connect this crossing the y-axis with crossing the x-axis with leaving the box in quadrant 3 without somehow turning around to make that happen. All right, so what they're saying is if you have a polynomial of degree n, you have at most n minus 1 turning points. So let's say you had degree 7. The maximum number of turning points would be 6. And if you had, let's say degree 4, maximum number of turning points would be 3. So degree 4 might look something like this. Why? Because even tells us which quadrants it leaves the box. and 1, 2, 3 turning points. Now the truth is it might not be degree 4, might be some other thing because these are just maximum numbers. So this could in theory be degree, it would still have to be even. So it could be degree 6. We don't know for sure that it's degree 4, but degree 4 and 1 minus that, so degree 3 turning points, might be our best guess for something like that. And that's what we're doing a lot. We're doing a lot of guessing when we're talking about these images. All right, so let's see. The question is this a polynomial? No, polynomials don't have gaps like this. They have to be continuous. So remember the two words, smooth and continuous. So this can't be a polynomial. And if it were a polynomial, yeah, we wouldn't even be able to, this isn't really a polynomial behavior either. It looks kind of, it should curve more, but like I said, calculus is in the business of measuring curvature. Here we go. This is the polynomial. Best guess, it's a polynomial of degree 3. That suggests odd function because it's like x cubed. 3 zeros is the number of zeros you might have for degree 3, but what we're just talking about, 2 turning points, is also an indication that it might be degree 3, but more specific or more general, just the look. It looks like a polynomial of degree 3. Not a polynomial. They're not flat like this, but more importantly, they don't have that little bump right there. They have to be smooth. This looks like definitely looks like a polynomial, right? I don't know. It looks a little straight right here. I'd be more comfortable if it curved a little more. All right, so they're saying the polynomial has to be at least degree 4. Do you see why? 1, 2, 3 turns. So degree 4, and degree 4 is a good guess, but they do have to say at least degree 4 because we don't know. Maybe something happens out here, but or maybe it doesn't have any more turning points, right? Well, let me give a quick example of that. Just why our favorite graph, y equals x cubed, doesn't have any turning points. It has this little thing where something happens, but it's not what we consider a turning point. So remember, this could have at most 2 turning points, but it doesn't have to have 2. It could have 0. And that's what they're trying to emphasize here. All right, I know it's a long section, but this is what I've been saying. The end behavior is how the graph leaves the box. So quadrant 1 maybe, quadrant 2, what quadrant leaves the box? The end behavior of the entire graph is the same as just the first term, just the power function. I'm not a fan of this. F of x, arrow infinity as x, they say approaches infinity. I just describe this as quadrant 1, and hopefully you understand what I'm saying. As x goes to the right, the function goes up. I describe this as leaving the box in quadrant 2. But this is the situation where you have an even exponent and a is positive. This is the situation where you have an even exponent, but a is negative. So I'll just put an example. Let's say minus 2x to the 4th plus some other stuff. If you had minus 2x to the 4th, you might expect something like this, because it's going to leave the box in that area. This one right here, quadrant 1, quadrant 3. And so that tells us that it's an odd polynomial. And again, the first term has a positive coefficient. So that might be 2x cubed and some other stuff. This one, When you leave the box this way, quadrant 2 and quadrant 4, it's this graph reflected with a minus because of a minus sign. So it'd be like saying minus 2x. I don't want to put 3 here because there's 1, 2, 3, 4 turning points. So maybe 2x to the 5. But it had to be odd, and the coefficient had to be negative. So we can use this as a graphing technique. As you've seen, we can use it for a lot of reasons, but just make sure you kind of understand the, we're ignoring what happens in the middle for the most part, and just looking at the behavior on the ends. And if you look at the behavior on the ends, it will reveal information about the lead coefficient, and worded the other way, the lead coefficient reveals how the graph behaves on the ends. That's what end behavior is talking about. So this is a multiple choice question, and possibly a multiple choice question with more than one answer. But basically we're going to use 2 facts on this. Just 2. I'm not really sure why the author brought this up, must be something he was, had in some calculus example and brought it up. But so what do we know? If this is a 5, we know that the box, and it's a positive 1 as the coefficient. We know it's going to leave in quadrant 1 and quadrant 3. So quadrant 1, quadrant 3. Well, it turns out all of them do that except this one. So that's ruled out just by looking at the 5. All right. Well, if it's if it's 5, what else? We know that there are at most 4 turning points. So 1, 2, 3, 4. 1, 2, 3, 4. And well, look at this one. 1, 2, 3, 4, 5, 6, 7, 8. This one gets excluded because of the turning point rule. Now the turning point, I'm using a number I haven't written down yet. It's this 5, but decreased by 1. So if n is 5, the number of turning points is n minus 1, which is 4. So you want to see that, right? And then the last thing is this. F of 0, we know is going to be 3. And the reason why is that even though I don't know what A and B are, if I put in a 0 here, a 0 here, a 0 here, a 0 here, if I put in a 0, all of those are zeros, and I get 3. So what's that ordered pair look like? It's up here between quadrants 1 and 2. That's what 0, 3 looks like. That is not 0, 3. That is 0, a negative number. So this gets excluded based on the y-intercept. The only possible one, the only survivor is this one. Now, like I said, there could have been more than one correct answer to this. In other words, if they had just drawn this a little differently where it, didn't cross here, or I don't know, it was just a different function, but it still maintained the major ideas. It could also have been a choice. So, well, anyhow, the author does it. Starts off with the intercept, and, wow, gets to that pretty quickly. All right. Now this time they're just asking us to come up with a function. They say use the smallest degree possible, so don't use some bigger number than you need to. All right, hopefully the first thing you notice is 1, 2, 3. I don't know if it has to be the first, but 3 turning points suggest that n minus 1 is 3, so n would be 4. And that's consistent with a polynomial that leaves the box in quadrant 1 and quadrant 2, meaning it's going to be an even exponent. And look, we have all these zeros just handed to us. -1, 1, and 2. So I'm just going to say x plus 1, x minus -1, x minus 1, and x minus 2 would be the a good starting point for this. But notice how it crossed here, it crossed here, but notice what it did here. It did that little thing that suggests that this is a polynomial, or this is a 0 of degree 2. So let's look at the author's analysis here. All right, so they found the intercepts, put them in parentheses, and then did the 3 turning points. All right, but more than that, I don't know, more than that. I haven't even confirmed that this was degree 4, but it is. That would be x squared times x, so it's already degree 4. But we weren't done when we just put them in parentheses. We had to address this issue, and we had to address the fact that we wanted the degree 4. So I think there's a typo here. 1 is not a multiple degree. It crosses there. Okay. I don't know if there's the typos in our book, but again, I mentioned I get these slides from the website. So putting the square on this guarantees that I'd get this touching without crossing at that point. If I put the square here, the graph would have touched without crossing here, and that would have been a very different graph. Okay, now they said we should find the lead coefficient, so how do we do that? Well, if you were to multiply this out, notice the constant term would be 2. The constant term tells us the intercept, and the intercept is not, in this image, is not 2, it's 4. So what would I have to do? I'd have to multiply this function by 2 to reconcile that last bit of information, as they did here. All right, one more example. We're running on battery too. Sorry. Plug in. I should pause this, but it should only take a second. Got a cable in front of me. All right. Well, just see how this graph matches to this graph. Just look at that. You can find the intercepts. This suggests -1. This suggests 1. This typo is bothering me. And this suggests 2. And you can use a graphing calculator to verify that. That's what they're saying here. Whew. All right. This will definitely be our longest section. This was just 5.1. I did it in 2 videos. But there's a lot of important information here. And I'll admit some of it is new, or at least maybe not all that new, but we're making connections that you hadn't had to knit together prior to this. So it's an important section because it's kind of the beginning of using some things that integrating some ideas that we hadn't seen before. So that is 5.